So now we'll look at some other aspects of bonding. The first one we're going to look at is what we call bond polarity. And bond polarity gets into the fact that when we look at molecules, not all electron sharing is equal. Or in other words, just because two atoms are sharing an electron or a pair of electrons doesn't mean that they're sharing them equally. And so we can look at two examples of molecules here. So here we have hydrogen, H2, and water. One of these molecules is what we would call a nonpolar covalent bond. In a nonpolar covalent bond, the electrons are shared equally. But in water, which is what we would say it is polar covalent, the electrons are not equally shared. Now, how do we determine this? So we now need to introduce a concept known as electronegativity. And you can see here is an electronegativity chart. So electronegativity is the ability of an atom to attract electrons. Now there's some similarity between this and something we talked about previously, which is electron affinity, but they're not exactly the same, and we want to be careful of that. But a couple of important trends that we want to be aware of before we start thinking about how this applies. So the first thing is fluorine. Fluorine is the most electronegative element. So when it comes to electronegativity, the higher the electronegativity is, the more that atom wants electrons. Where do we find our least electronegative element? At the opposite end, francium, 0.7. So electronegativity increases to the right and increases going up. So again, we find our most electronegative element up here at the top right and least at the bottom left. So let's keep a couple of these numbers in mind when we go back to our previous example, which was hydrogen and water. So note the electronegativity for hydrogen is 2.2 and 3.44 for oxygen. So if we look at H2, clearly we have the same atom bonded to itself. It's two hydrogens. And so what we would consider is what is the difference in electronegativity between the two elements. As long as that difference is small, usually less than 0.4, although you may see this reported as 0.3 or 0.5, It isn't a hard, fast boundary on this number. It's just kind of a general range. But if this number, this difference in electronegativity is small, that means the two atoms that are bonded to each other are equal in their ability to attract electrons. So they're going to be tugging on those electrons pretty much at the same amount. And so we're going to end up with relatively equal sharing here. And so that's our nonpolar covalent. What about when we go to water? Well, now we have a difference in electronegativity of 1.24. That's because oxygen is much more able to attract electrons. So these oxygen-hydrogen bonds are what we would call polarized towards the oxygen. So we would say here the electrons have unequal sharing. And therefore water is made up of polar covalent bonds. And so polar covalent we typically find when the difference in electronegativity is less than about 2, but greater than about 0.4. Well, what if the difference in electronegativity is more than 2? Well, let's think about what it would take for that to happen. So think about it for a minute and see if you can find some pairs of elements that have a difference of electronegativity of 2 or more. Now, what you've probably noticed in any of those pairs that you've chosen where the difference in electronegativity is that high, you have a metal and a nonmetal. And so for a high difference in electronegativity, again, greater than 2, you may see this in some sources greater than 1.7. Again, it's going to be a little bit different in different sources. But typically, if you have this very high difference, that's what leads to an ionic bond. Now, within a molecule, just because a molecule has polar bonds doesn't mean that the entire molecule is polar. Turns out those are two different things. And what also comes into play is geometry. So what is the shape of a molecule? So I'm going to do the best that I can to get through this section. The biggest issue we have is this is a topic that when I cover in person, I always do this with my model kits. And unfortunately, I don't have any of my model kits with me at home, and I'm not able at this time to get back into my office to pick those up. But in a couple weeks that you'll be doing a lab experiment. It's actually the easiest experiment of the term to do at home because it's a dry lab. But you'll be doing some computer simulations that will greatly help you to see what these shapes look like. Again, we have representations for all of them in 2 dimensions, and that's what I'm going to use here. But just sort of a heads up, this is always one of those lectures that's much, much better with a model kit. So the geometry of an atom is determined by this theory, which we call VSEPR or VSEPR, that stands for valence shell electron pair repulsion. What that means is that in general, electrons don't like each other. And so electrons try to stay as far away from each other as possible. The electrons do not want to be near each other at all. So what determines the geometry? Well, 2 things for any atom. How many atoms it's bonded to, and the number of lone pairs. So if we look at any atom and we can see how many atoms are bonded to it and how many lone pairs it has, then we know what the shape of that molecule is going to be. Note, I said only the number of bonded atoms. The type of bond, double bond, single bond, triple bond, does not actually matter. So before we get into these specific geometries, we have a term that we want to define, which is the term electron domain. And so 1 electron domain is equal to any bond. That can be a single bond, double bond, or triple bond, or a lone pair. Again, the type of bond doesn't matter. So a single bond is 1 electron domain, a double bond is 1 electron domain, a triple bond is 1 electron domain. It just matters how many different atoms it's bonded to. So let's just look at a couple of examples here to clarify that. So if we think back to some of the Lewis structures we've drawn, here's carbon tetrachloride, here's ammonia, let's do formaldehyde, and let's do hydrogen cyanide. So how many electron domains do each of these atoms have? So this carbon in carbon tetrachloride has 4 single bonds. It has no lone pairs, so this carbon has 4 domains. In our next molecule, ammonia, the nitrogen has 3 single bonds and 1 lone pair. Each one of those is its own domain, so that's also 4 electron domains. For formaldehyde, the carbon has 1 bond here, a second bond here, and a double bond. So how many electron domains is that? Well, it's only bonded to 3 atoms. Even though one of them is a double bond, that's still 3 domains. Same type of situation in hydrogen cyanide. 1 bond, and then bonded to a second atom. So a total of 2 domains. And so if we know the number of electron domains, the number of bonds, and the number of lone pairs, we can predict the geometry of any atom. Why would we want to do that? And why would that matter? Well, perhaps the best story, or worst story, is this molecule here. This is known as thalidomide. Because of the geometry of carbon, carbon has some very, very interesting properties. And if you take organic chemistry, we'll get into those in that course. But because of the geometry of carbon, thalidomide exists as 2 possible compounds. And you can see the difference in them here. So when we have one of these wedges, that means the bond is pointing toward you, or out of the plane. When the bond is dashed, it's pointing away from you, or back into the paper. Thalidomide was a drug that was prescribed, it probably goes back 60 or 70 years now, because it was found to be very effective at treating morning sickness. Unfortunately, they found out that while one of them works extremely well, the other leads to some rather severe birth defects. And it's one of those things that I would be careful about looking up on the internet. You'll certainly find things, but if you do, some of the graphics may be disturbing. But led to some very, very severe birth defects. And they tried to see, was there any way that they could just administer the safe one as a drug? And it became pretty clear that this molecule actually does some very interesting things biologically. And so no, you couldn't only give someone one of them. And so they obviously had to stop using it to treat morning sickness. But all of this is based on bond geometry. One more example like that. This one's definitely less tragic and maybe more familiar to you. These are Carvones. Again, it has this special property that we saw of carbon down here. And one of these compounds is spearmint, and the other one is caraway. So this idea of geometry of molecules, we've seen one case where it had very severe and very tragic consequences. This one's much more interesting. This is something we might run into every day, or in our everyday life, outside of a chemistry course. And there's many, many other examples like this. So in the next video, we're going to start talking about specific geometries. What are the geometries that molecules actually adopt?